In this question, we have this truck which is moving on a linear path, and then it has a speed of 40 kilometers per hour, and it has an acceleration which is in the negative direction to its motion, so we call it decelerating at a rate of 3 meters per second squared. So there is the linear motion of this truck. That means at any point on this truck, the velocity and acceleration that we're going to measure will be the same, except the ladder, because the ladder here has a relative motion with respect to the truck. But the other parts, as assuming this truck to be rigid enough, would have the same velocity. That goes for B point as well. That means velocity of B is actually equal to 60 kilometers per hour, and its acceleration of B is equal to 3 meters per second square. If we want to change this into meters per second square, we need to multiply this 60 with 1000 and then divide by 60 for minutes, and then another 60 for change this information to seconds. And then we're going to receive the meters per second information from this calculation. Anyways, this is the information about this truck. Now, let's take a look at what we have for the ladder. There's a state angle defined of the ladder with respect to the truck, and then at the instant theta angle is given to us as 30 degrees. However, it is increasing at a constant rate. That means theta dot, which is equal to the omega angular speed, is 10 radians per second, or 10 degrees per second. So this is degrees per second. We need to change that to radians per second. In our calculations, we always use the radians per second. In SI units, this is how we use it. So, oops. This is going to be equal to 10 times oops, 10 times pi over 180, and this is the way we change this from degrees per second to radians per second. This is radians per second. And theta double dot, or omega dot, which is equal to the angular acceleration of this ladder, is 0, since this is the angular velocity is defined as a constant rate. Then there's this extension of this ladder, and it is defined by this variable length b. Now b at the moment is 1.5 meters, but it is increasing. The length is increasing by 0.6 seconds, 0.6 meters per second, and then the increase has a decelerating acceleration, or the speed of this increase is decelerating because it needs to come to a full stop at the end. It's extending, but then it needs to come to a stop because it cannot extend forever. Then at that instant, it is measured as negative 0.3 meters per second squared. Now what happens here is, if we define a frame here along the ladder in this way, this whole thing happens about the x-axis. This extension of B happens along the x-axis. And this x-axis is rotating with respect to our inertial frame. So we call this capital X-axis of the inertial frame, with the state angle and with an omega speed of 10 degrees per second. So we have a general case here for investigating a motion of a body with respect to a rotating frame. There's our frame, it's rotating with respect to truck. Truck has a velocity and a zero acceleration. Now let's take a look at what we are expected to find in this problem. we are expected to find the acceleration of point A, this is the tip of this ladder, with respect to the track. So what we are talking about is the acceleration of A relative to B, and also we are expected to find it with respect to the ground. That means we are expecting in the B case to find the absolute acceleration of A. In fact, absolute acceleration of A is just equal to AB plus A acceleration of A relative to B. Let's just show our vectors here because these are vector equations. This is a vector equation. There's our vector equation. Okay, so the velocity of B and acceleration of B are all defined in this capital extraction. But then we can resolve all that velocities in these xy frames. How can we do that? By making use of this theta angle. Velocity of B actually can be resolved as, again, this is again the same thing for the acceleration of B, but it can be resolved as there's this velocity of B in this direction. So it's going to have a component in the x direction, which is basically in the cosine direction. Velocity of B cosine theta, and this is in the positive I direction. And then if we take a look at the component of this velocity in the y direction of this plane, it is actually in the negative direction, negative y direction. And the way that we can calculate that is by negative the magnitude of B sine theta j. There's our resolution of the velocity vector for the B point in this xy plane on the level. And also acceleration of B would be in the same manner, just exchange this VB to AB, and then you will find that information. Okay. That being said, now our common equation is written out like this. There's this absolute acceleration of B and then relative acceleration of A with respect to B. In the first part of the question, we are asked to find this part, and that part is actually composed of two parts. If you would like to solve this question in this way, you can imagine an imaginary point P and then define its acceleration with respect to B, and that is composed of these extra terms that appears in the rigid body equation. There's the tangential part, there's the normal part, and then plus the acceleration of A with respect to P, there's the Coriolis part, and there's the relative motion part. Again, you can just write these out as four terms side by side, and then you will get the relative acceleration of A with respect to B. Now, what are we missing here is actually alpha is equal to 0. So this part is gone. Omega is defined here. Omega is always in the k direction. So if you defined already this is x and y, z is going out of the board. So this is defined. R is the vector here defined from B to A point. Okay, and with respect to our selected frame, this is actually equal to 6 meters plus B, and at that instant B is 1.5. This is as a result of that 7.5 in the I direction. 7.5 meters in the I direction. This R, yeah, it becomes that. What else? Omega, we already specified omega. V relative. V relative is the relative velocity of this A point relative to B, and here we have the relative motion defined as B dot, and it is in the I direction. So this V relative is defined as 0.6, and its direction is I. What else? We need to find A relative. The acceleration of that A is defined with B double dot, And this is equal to, in that sense, because we have a minus sign, we need to keep that minus sign, 0.3 in the I direction as well. It cannot be in another direction, right? This frame is attached to the ladder and rotating with the ladder, so it will be always in the I direction, this acceleration of extension. Therefore, we have all the information. We just need to plug in this information in our equation, and the equation is right over here. This is the first part, A, acceleration of P with respect to B, plus acceleration of A with respect to P. The rest is just writing out all these parts, and then we find out the acceleration of A with respect to P in this way. This is in meters per second squared. Then the acceleration of B, the absolute value of the acceleration, is shown here as it is calculated. And this is exactly the same thing that I have described here for this velocity term. There is this velocity of B cosine I. And then here we have a negative 3 here because the truck is decelerating, right? Let's take a look at that information again. Truck is decelerating, so we have a negative sign for the acceleration, negative 3 meters per second squared. This is why we have negative 3 here. And this is the resolution of this vector, which is in the x direction of this inertial frame. As resolved in our new frame, xy frame, it will get a plus cosine theta and a minus sine theta. Plus cosine theta is in the I direction. Negative sine theta is in the j direction. So that's what we have here as plus cosine 30 degrees as a theta in the I direction and a negative sine 30 in the j direction. And then if we add these two vectors up, this is our resultant for the absolute acceleration of the A point. And this is resolved in the frame that is attached to the ladder. You can later choose a different frame and then you can resolve it in a different frame. But at the end of the day, this is just a vector. It lives on its own. This is its definition in one frame. You can define it in another frame if you want.